Discrete event simulation is a powerful modeling and analysis technique used to study complex systems that evolve over time. It is particularly useful for understanding and optimizing systems where events occur at discrete points in time, rather than continuously. Discrete event simulation is widely applied in fields such as manufacturing, healthcare, transportation, logistics, telecommunications, and service industries. The modeling technique used to represent systems as sequences of discrete events occurring at specific points in time. Each event marks a change in the system's state, while the system remains static between events. This approach is particularly suited for dynamic and stochastic systems where continuous simulation methods may not be practical. The models rely on fundamental concepts such as entities, queues, servers, and gates to simulate processes like customer arrivals at a bank or product flows in supply chains. By focusing on discrete occurrences rather than continuous changes, the approach simplifies complex systems, enabling analysts to study latency, resource utilization, bottlenecks, and other operational metrics effectively. In this lecture, we will be focusing on how discrete event simulation are used in the banking operations system. Banks face numerous operational challenges that can significantly impact efficiency and customer satisfaction. Long waiting times, especially during peak hours, are a common issue, often leading to customer dissatisfaction. Efficient resource allocation is another challenge, balancing the number of tellers, ATMs, and staff to meet fluctuating demand requires strategic planning. Operational costs pose further complications. Overstaffing leads to unnecessary expenses, while understaffing can degrade service quality. Additionally, banks must manage uncertainty due to variability in customer arrival rates and transaction durations. These challenges necessitate robust solutions that can adapt to changing conditions and provide actionable insights. A successful discrete event simulation model for banks requires defining core components that represent the dynamic interactions between customers, resources, and events. Entities. Customers represent individuals visiting the bank for various services such as deposits, withdrawals, or account inquiries. Tellers or staff represent service providers who manage customer requests. The number of tellers directly impacts service speed and customer satisfaction. Events. Events are key occurrences that change the state of the simulation. Common events include: customer arrival marks the entry of a new customer into the bank. Service start indicates when a teller begins serving a customer. Service completion signals the end of a customer's interaction with the teller. Customer departure occurs when a customer exits the bank after completing their transactions. Resources. Teller counters, limited stations where tellers serve customers. Waiting area, a queue where customers wait if no teller is available. Attributes. To build an accurate simulation, key parameters such as arrival rates, service times, and queue behavior must be defined. Inter-arrival time, the time interval between consecutive customer arrivals. Service time, the duration required for a teller to serve a customer. Queue discipline determines the order of customer service. Most banks follow a first-in first-out or FIFO queue system. A simple discrete event simulation of the banking process at the customer desk is shown in this study. It illustrates a bank queue simulation interface designed to model and analyze the flow of customers through a bank's service system. This simulation interface includes multiple interactive elements, visual displays, and summary statistics that provide insights into queue management and service efficiency. The upper section of the interface features a control panel equipped with various adjustable sliders. These sliders allow users to configure key simulation parameters such as the total simulation duration, the average arrival rate of customers, the average service time per customer, and the number of active service points. In the displayed scenario, the simulation time is set to 600 minutes, representing a 10-hour operational period. The average customer arrival rate is adjusted to 0.5 customers per minute, while the average service time is configured at 1.3 minutes per customer. Additionally, the number of available service points is set to 1, meaning only one active counter is handling incoming customers. The control panel also includes Start Simulation and Stop Simulation buttons, allowing users to initiate or terminate the simulation process. In the middle section of the interface, a graphical representation of the queue is displayed. This section shows the current state of the queue with 3 red customer icons labeled 31, which likely represent individual customer numbers. Adjacent to the queue visualization is a service point marked as service with a blue icon labeled 30, indicating a customer currently being attended to. This visual feature helps users understand the real-time status of the system, including the number of customers in line and those actively being served. The right side of the interface presents a detailed summary of the simulation results. Key metrics include the total simulation duration, which is confirmed to be 600 minutes. During this period, the system successfully served 312 customers. The maximum queue length reached 8, suggesting that while the system experienced occasional congestion, it remained manageable. Notably, the average wait time is recorded as 0.0 minutes, which indicates either an efficient queue management system or a relatively low arrival rate that allowed most customers to be served promptly. Furthermore, the service point utilization is reported to be 65.2%, reflecting that the service counter was active for approximately 2/3 of the total simulation time. Discrete event simulation offers several applications that address these challenges effectively. One primary use is queue management, where DES simulates customer arrivals and waiting times to optimize queue lengths and determine the ideal number of tellers or counters. Staff scheduling benefits from DES by analyzing workload patterns to ensure efficient staffing, reducing idle time while maintaining adequate coverage during peak hours. Banks also use DES to optimize ATM and self-service kiosks by modeling usage patterns to decide the optimal number and placement of ATMs. Furthermore, DES assists in branch layout design, testing different configurations to minimize congestion and improve customer flow, identifying potential bottlenecks. Lastly, scenario testing through DES enables banks to simulate what-if situations, such as increased customer traffic or new services, predicting system behavior under varying conditions.